I want to welcome everybody tonight. And it's my pleasure to introduce tonight's speaker, Dr. Kimberly Ennico-Smith. And she is a research astrophysicist and planetary scientist at NASA Ames Research Center in Silicon Valley. She is multidisciplinary in her approach to space instruments, telescopes, and mission concepts. She has designed and built infrared airborne and space telescope cameras and spectrometers, tested detectors in laboratories and particle accelerators, designed low-cost suborbital instruments, and built lunar payrolls. She has served as project scientist for the Flying Infrared Observatory SOFIA and deputy project scientist of New Horizons Pluto flyby mission. She's been a member of the Science and Technology Definition Team for the Origin Space Telescope. Asteroid 154587 Ennico is named for her. Since 2020, she is deputy project scientist for NASA's Viper Lunar Volatiles Rover, which we're going to be hearing about tonight. So with that, I will turn it over to our speaker, Kimberly. The screen is yours.
All right, thank you. Thank you for inviting me. Give me a moment so I can share my screen. I'll speak on behalf of a team I work with to introduce you NASA's next lunar rover called Viper. And I often find when I start a talk, can I tell the talk in 30 seconds? So I made a cartoon. So NASA is sending a mobile robot to the surface of the south pole of the moon, a place we've never visited before. Her name is Viper, which stands for the Volatiles Investigating Polar Exploration Rover. This explorer will give us our first close-up views of the location and concentration of water ice, whose presence on the moon was only discovered these last few decades, and we still have so many questions about it. Data from Viper will generate our first water resource maps. The moon's south pole is also where humans will land under the Artemis program. Water is extremely critical for deep space exploration. It is a resource of direct value for humans as it can be turned into oxygen to breathe and serve as a fuel supply. Viper will bring us significant steps closer to NASA's ultimate goal of a long-term human presence on the moon and make it possible to explore Mars and beyond, expanding knowledge and technology for the benefit of humanity and Earth. That's the story. No. So I entitled it The Next Great Leap in Understanding Water on the Moon. But I think we have to go back a little further. Our story begins in 1609. This is the first leap. This is perhaps the first recorded impression of the moon through a telescope, the first realistic depiction of the moon in history. So it's Galileo draws his observations. He discovers that the moon has mountains, pits, and other features just like on Earth. The moon is not smooth, which had been thought for eons. So Galileo kept an open mind. He remained curious, and in doing so, he challenged the thinking around him and pushed our knowledge of the universe. You're an astronomical society and have star parties and that, reflect back to the first time you looked at the moon with a binocular or a small telescope. And how did you feel? Significant leap. So speaking of star parties, my skies in Boulder are cloudy tonight, but from San Mateo, if your night sky is clear, the moon is at the waxing gibbous phase. It's risen in the east around mid-afternoon. It's remained high in the eastern sky, and it'll be visible through most of the night, and it will set a little bit in the west before sunrise. The image you see here is from a program called Stellarium, it's a free open source planetarium program for your home computer. So I set it to show what the moon would look like from San Mateo, California at 9 p.m. local time tonight. So as our theme is tonight is water on the moon, how about a nod to moon water, but in the wrong sense? On the near side of the moon, the side that faces us here on Earth, the most notable features are these mare, these dark areas on the moon, flat plains of lower elevation. Now they were named, mare is Latin for seas, and so they were named erroneously by 17th century Western astronomers because they thought they contained water. but they're very dry. So let's move on to our second leap, 1969, when we have the physical exploration of the moon. Stand by for a second. That's my mouse. So in 1969, or actually technically, we began to do the physical exploration of the moon in 1959 with the Soviet Luna 2 mission, which made the first hard landing. This would follow several robotic missions, including the famous human landings between 1969 and 1972. The photo shown here is one of my favorites. It's Pete Conrad Jr., Apollo 12 commander. He is examining the Surveyor 3 spacecraft. Now, Apollo 12 visited the moon in November of 1969. Surveyor 3 robotic came before about 2.5 years earlier, April of 1967. It's a wonderful story of using robotic explorers to sort of check out the lay of the land, followed by humans. And if you have eagle eyes, you can see the intrepid lunar module in the top right. In the second leap of learning about the moon, where did those early explorers go? So this is just showing the first generation of explorers landing on the moon in those early in the 60s and 70s. And although the regions that were explored at the time covered maybe at most 4% of the surface area, we learned an incredible amount about our nearest neighbor. In our story of water on the moon pretty much got a dry reputation. Analysis at the time of the rocks brought back by the robots and the human explorers showed no evidence of water. At the same time, the analysis of those same rocks informed us that the Earth and the moon are made of similar material. This led to the giant impact hypothesis, where the concept of the moon's origin formed from the debris of a collision of the early Earth, and a Mars-sized object about 4.5 billion years ago. That impact was so fiery, the scientists suspected that any water, whether it came from the Earth or the mystery object, would have boiled away for good. So the moon had a dry reputation. Our third leap is the next chapter of the story, is water is discovered on the moon, and potentially in large quantities at the poles. Its presence continues to challenge the theorists who for decades have computed that the moon should be bone dry. So after the Apollo missions ended in 1972, we never stopped exploring the moon. Enter now the next gen, the series of robotic explorers of the 1990s with more modern instrumentation that measured new minerals and whose orbits took us closer look at areas of the moon we hadn't really explored before, such as the lunar poles. Clementine in 1994 did a bistatic radar test, bouncing radar off the surface of the moon, and revealed a curious finding at the poles, which could indicate superficial water ice. Yet the signal was also consistent with it just being a rocky surface. So it was an inconclusive experiment. 5 years later, another satellite, the Lunar Prospector, made measurements of neutrons, gamma rays, electrons, alpha particles emitting from the moon. In particular, the neutron measurements had revealed that the shadowed craters at the both poles contained elevated hydrogen. This stirred an incredible new dialogue in the community. And this was the data set that opened up a new dialogue. So what's shown here is a projection of the two poles, North Pole on the left and South Pole on the right. And they showed distinct elevation and amounts of hydrogen. Technically, the instrument aboard the spacecraft measured neutrons. Neutrons are constantly coming out of the lunar soil. And when the neutrons hit something about their size, like a hydrogen atom, they lose a lot of their energy. So the instrument aboard this spacecraft measured a suppression of neutrons at both poles, which in turn suggests the presence of large amounts of hydrogen. So in the picture, purple indicates high amounts of hydrogen or low amounts of neutrons from the actual measurement. So it was quite a stunning discovery. So staying true to the spirit of Galileo, the community stayed curious and had an open mind. And this led to a series of more missions in the early 2000s to measure the hydrogen, to reassess the mineralogy of the moon. And one mission in particular did a specific test. To test to see whether hydrogen was in the form of water. Water is H2O. That mission was an impact experiment called LCROSS. And I worked on that. I was very honored to have had that opportunity. We deliberately crashed the upper stage of a rocket. It's shown artistically in the top left. It's about a school bus size impactor into the moon, 5,600 miles per hour, into a permanently shadowed crater on the moon. And we were targeting one of those purple areas. We tossed up 4 to 6 tons of soil and we made a crater. And we had spectrometers on board, and they measured water vapor, water ice, carbon monoxide, ammonia, methane, organics, and a whole bunch of other things. I remember when an article came out about our discoveries, it said you had just basically hit a garbage dump of the moon, because we found a lot of things in the basin of that crater. The mission was a game changer in our story of water on the moon, because we now have the first direct evidence, at least in one spot, that a strong hydrogen signature in a cold location on the moon contained a lot of water ice. So getting back to our next gen fleet, it's an international fleet of missions and have continued to reveal more information about lunar water. We have the NASA's Lunar Reconnaissance Orbiter still orbiting the moon today. It's provide global topography at 100 meters per pixel, in some areas down to 1 meter per pixel. We have global surface temperatures of the moon day and night. And we've learned that regions that get little or no sunlight are very cold, even colder than the surface of Pluto. And we've learned that the ultraviolet reflected light from the basins of craters are representative of surface ice. The Indian Space Agency has flown 2 orbiters, the Chandrayaan-1 and 2, carried a near-infrared spectrometer, and they measured surface water presence spectroscopy by reflection off of sunlight. And now we've made global maps of water on the moon. But they found that the concentrations were closer to the poles and less at the equatorial. So we've had the Kaguya, the Japanese Space Agency Kaguya mission that has provided us with updated maps of the moon's mineralogy. And most recently, the Chinese Chang'e missions, which include 2 rovers and they've done a sample return, have been exploring the moon and adding more information about our story. So today, the moon has lost its dry reputation. We have learned that the water concentrations on the moon are not uniform. These are references to papers that have been published based on the Chandrayaan M-cubed data. We have learned that the strong hydrogen signatures at the poles are consistent with other measurements of water ice, although we have to admit they are sometimes not so self-consistent. So they've offered us a lot of questions. We know that we've detected the presence of water in one particular spot very deep in the shadow of a crater at the lunar South Pole. In the last couple of years, the Sophia Airborne Observatory has actually observed water on the surface of the moon in the daylight. That's a very exciting discovery. This water might be a different type of water in terms of it's more in glass beads. And then reanalysis of the Apollo lunar rocks have revealed that there is water inside those rocks as well. Most likely the water source is from the lunar interior. But this is a testament to sample return and the fact that 40 years later, our instruments in laboratories on Earth are much better and much more sensitive. And we can find that there are water in the Apollo samples. And a paper that just came out like 2 weeks ago on the Chang'e 5 lander actually has measured the presence of water on a rock through infrared spectroscopy. Again, we're just finding that water is in a lot of places on the moon. It's very dynamic conversation. So a moment ago, I used the term permanently shadowed crater or permanently shadowed region. Didn't really get to define it. So this is an illustration of what I'll attempt to describe. You're seeing the moon and the numbers represent the Apollo landing sites. The video is going to move and show us going towards the lunar South Pole. The illumination conditions at both poles are extremely different. And this is due to the geometry of how the sun is with respect to the lunar horizon. At both poles, the sun gets only a few degrees above the horizon. So it creates a geometry where long shadows are cast by the topography. Shadows at the poles can be 100 miles long. And so I just encourage you to stare at one place on this image, and you can see how the shadows are moving. In some places, the shadows never leave. And those regions in permanent darkness are the permanently shadowed craters or permanent shadowed regions. And without the sunlight, these regions are very cold and may have been cold for the entire geological history of the moon itself. So the poles provide this geometry to have lots of areas that are cold. And when it gets a little bit later in the story, why is that important? That's just a short introduction to permanently shadowed regions at the polar regions. And there are permanently shadowed regions at both poles. Okay. So we get to the next leap. 2023, which is the date of our rover's launch. So we're about to start this next leap in the moon water story, ground truthing those orbital data sets, and then mapping the moon at rover or human scales to assess how much water is there and is it accessible. So this next leap is the motivation for Viper, the Volatiles Investigating Polar Exploration Rover. We are driven by two science goals: to characterize the distribution and physical state of lunar polar water and other volatiles in lunar cold traps and the regolith, which is the lunar soil, to understand their origin, and to provide the data necessary for NASA to evaluate the potential return for in situ resource utilization, or ISRU, from the lunar polar regions. So our rover is about the size of a golf cart, and it roves within a demanding lighting environment. I was mentioning those long shadows, 100 miles long. The dramatic lighting environment has sharp contrast and these shadows, and there's unknown rocks and crater hazards because we've never sent a rover to the lunar polar regions, and our knowledge of the terrain is only good to the hundreds of meters scale, and our rover is 1.5, 2 meters big. So we have no knowledge of anything that the rover is going to be driving around. So as a challenge, we have to carry lots of lights. In fact, this may be, with the exception of, so the Apollo missions landed during the daytime, they didn't have to carry any lights. So we have lights on our rovers because we're going to be driving in the dark and have to observe in shadows and where we don't have much light. So we have lights and on mass to do 360 degrees. We have cameras at the back, cameras and lights in the wheels. The nature of the soil, the regolith, is unknown. Is it hard? Is it soft? Is it churned up? Is it even drivable? So each wheel for this rover has been designed with a unique type of mobility. Shown are some animation, well, test images of concepts of the wheels during development. The top one does sort of a stretching and squatting mode. That's to get around rocks as it's driving around, to get up and down around rocks. We're expecting when we go to some of these older regions that might have the ice, that the soil might be like sand and we might need to swim. And so the wheels are designed to help us climb out of very, what we call, very light and fluffy soil. Again, we have no idea, so we have to design a rover that's very agile. The Earth, as seen from the lunar poles, also doesn't get much above the horizon. So this is going to be challenging for our communications. We are tele-robotically driving the rover, so we're driving it from Earth. And so we need a direct line of sight. But the Earth will set below the horizon, and then we'll have to sit and wait until the Earth comes back. But the Earth is quite low on the horizon. I had mentioned that the sun is low on the horizon as well. We are a solar powered rover, and we have batteries to help us survive about at a minimum of 50 hours in total darkness. But although sun is low to the horizon, sunlight does get to the lunar poles, and it will get to our rover as well. I'm going to show here a time lapse of the motion of shadows shown in dark gray. And this is an animation of a possible rover path, which is, I think is shown with the red arrow that's moving that around. The speed of our rover is about the same speed as the speed of the shadows. So we're chasing the shadows, or actually we're chasing the sunlight, and the shadows come up behind us. So during this very dynamic mission, we are hunting for light and also going in and out of shadows. And we're carrying batteries to survive the dark periods. And another challenging environment, we're going to a cold place. Yet, so we're going to go to these permanently shadowed regions, could get down to 40 Kelvin, although, it depends upon where we're going to dip our toe in. But we also need to sunbathe, because we do need to charge our solar panels. So we'll have to experience a huge range of thermal environments. And so we have heaters to keep our electronics warm, and then we have to dump that heat as well. So it is a very interesting rover design for the unique challenges of lunar polar exploration at the poles. So it's a pretty cool rover. And it adds to our interplanetary robotic family. From a speed perspective, we're about 5 times faster than the current generation of Mars rovers, but we're way slower than the Soviet Lunokhod rovers of the 1960s. And I'll describe our speed a little bit more, but it's an interesting trade. The speed was the compromise by the fact that we have to drive fast enough to get the mileage to do our mapping, but we have to go slow enough so we can get statistics and the signal along the way. So we're going to make these measurements. So moving on from the rover to the heart of the mission, which is my loves, the science instruments, because I like building things. Viper's measurement and mapping concept has evolved over the years. It's built upon years of analog missions. We've put together a rover with a suite of different instruments and used them operationally on the Earth. In fact, we used to, in the Mojave Desert, we actually buried water and tried to find water in using different types of combinations. So what I'm going to describe today builds upon that experience. So the instruments aboard Viper are the following. We have a neutron spectrometer that sticks out front. This is our bloodhound, or a hydrogen divining rod. I mentioned earlier about the orbital mission that found the neutron suppression at the poles, which was indicated of high amounts of hydrogen. Well, we're putting a similar instrument on the rover, but we're at the rover scale. So it's going to look for large amounts of water, and it's going to specifically look for where there isn't any neutrons. We're carrying a near-infrared spectrometer that's looking at the surface, and that could identify the water and water equivalents and other volatiles spectroscopically. In the same field of view as this near-infrared spectrometer, we have a visible camera and a thermal radiometer to measure the surface temperature. Measuring the surface temperature simultaneously with the spectra has been a key lesson learned from the Indian orbital instrument M-Cubed had issues trying to fit the thermal radiation that they didn't measure, and model it, because this affects the depths of the features. So we're learning from all the missions that have gone before us. And then we're carrying a mass spectrometer. So a mass spectrometer distinguishes the different types of masses of elements and molecules. This one in particular has this, can sense between 1 and 70 AMU, atomic mass units. So we can distinguish between hydrogen, H2, which is 2 AMU, hydroxyl, OH, which is 17 AMU, water, H2O, which is 18 AMU, and it can explore isotopes. Isotopes are molecules that have different numbers of neutrons compared to their sister molecules. And so they can tell us about the origin of the water. And then finally, we have a drill to dig down to 1 meter in 10 centimeter bites, and will help us measure the subsurface temperature. So the Viper mission is this delicate recipe of the rover to get the mobility, those overlapping of science capabilities, and geospatial modeling, which I'll touch on next. So the design of the mission is encompassed among these science measurements, the sensitivity, how we're covering things, the length scales of our measurements, the variability that we're observing, and the sampling. And these are mapped to specific observables. So we think we have the right approach. We know there's going to be surprises. We are following a mapping approach that has been developed here on Earth by the USGS, the Geological Society, because when they go out to quantify something new, or maybe something known in a previously unmapped area, they have approaches. So we have on our science team, our scientists from the USGS who are helping us with the geostatistical approach to when you're trying to map something for the very first time and map something in an unfamiliar terrain. So let me tell you a little bit about this mapping approach, because I find it fascinating. It's not my background, but it's very intriguing. It's taking out the luck of prospecting and putting it into a mathematical and a probabilistic, a statistical approach. So our strategy is based on using temperature as a proxy. So the mission is to ground truth where the water is and how much of it is. So the evidence gathered to date, cold temperature is a good indication that water and these other volatiles will stick around. After all, volatile means it easily goes into the gas state and escapes. So thermal modeling, the theorists of the lunar soil have predicted that the subsurface, even down to just a few tens of centimeters, can get pretty cold. And this is when the surface may be in sunlight. So the Viper mission is, the mapping part is planned around the ice stability region concept, ISR. This is where models predict temperatures at or below the temperature where its water is in its frozen state, which is less than, say, 110 Kelvin, and has been that cold over geological timeframes. So, and additionally, we need to take into account the other processes that may be affecting the moon's water cycle. So we can start to talk about the moon's water cycle now, because there's all this other evidence about the interplay between how water got to the moon, how it's surviving, etc. But let's get back to the ice stability regions. We've broken it into 4 categories. There's the surface, shown in red on the left image, which is a model of where water ice could be present. A surface is like surface frost. It's water is in the ice form on the surface. So we anticipate this is going to be in those permanently shadowed craters and regions. And we want to test that hypothesis. We're going to drive into these. There's the shallow region shown in green, where water ice might be present in the top 0 to 50 centimeters. This is a very active area of modeling today, because the moon has been pummeled by micrometeorites throughout its history, and there's a churning of the soil. So it can keep ice around by burying ice that had been on the surface and now it's buried. Or it can excavate buried ice, and if it gets to the surface, it will vaporize into the sunlight. So actually knowing what is going on in those top 10, 20, 30 centimeters will validate or invalidate a whole bunch of models that are in the literature today. Then we have the deep. The deep is where water ice might be present between 50 centimeters and 100 centimeters. Now, we'd love to go deeper. In fact, there are many lunar theorists out there who hypothesize that the ice on the moon is buried way deep, much, much deeper. This 1 meter cutoff was chosen for Viper for scientifically and ISRU friendliness. So there are many ways to excavate buried lunar water ice. The 1 meter depth seemed to be, on average, the depth to which a lot of technologies can excavate the water ice. And then there's the dry. The dry just means the water ice is either not there or it's below 1 meter. And so by us measuring these different terrains, we can ground truth these predictions. So I introduced our anchor of our modeling and mapping concept. So we have to map strategically. What's shown here is a possible rover traverse. The science team right now is studying a whole bunch of these. I'm using the same color scales as the previous slide, where the surface ice is in red, the predicted surface ice. These are all kind of predictions. The shallow is in green, the deep is in yellow, and the dry is shown in gray. The light green circles are just telling you a distance from a landing site. And the innermost circle is 100 meters and the outermost circle is about 3 kilometers. So our little rover would traverse across this path. And this one in particular is about 8.2 miles over 91 Earth days. We have to pause at the end of a lunar day when the Earth goes below the horizon, and then we resume our path. So the key bit here is we want to visit the 4 ISR types and multiple times. So you have a puzzle in front of you to find the best way to visit places of scientific needs for the mapping, do it within the sunlight and the calm, and also be able to keep everything safe and collect the data. So our speed is about 10 centimeters per second. And what's also happening during the mission, we get the movie started a bit. Our rover is the prospecting and the instruments are on. So the scientists in the operations console will be getting near real-time data of the amount of hydrogen, the presence or absence of surface water ice, and surface temperature. we will get immediate indication of where reality matches predictions and where it does not. Then the team can react and replan where the rover should go next. So the three instruments during this prospecting phase do work together. So here's a schematic of the trends the science team will be looking for as the rover is driving. The rover is moving from left to right in this image. The yellow curve is measuring surface temperature, and it's gone low when the rover apparently went over perhaps surface ice. The light blue curve shows a band strength of a water molecule, and it peaks, coincidentally, also giving us evidence that, aha, we must have driven over ice. The red curve is measuring those neutrons, and I keep on talking about those neutrons. The neutron counts are starting to get depleted, so that's indicative of hydrogen, but we can't tell whether that hydrogen is on the surface or buried. And as the rover leaves the frost area, the neutrons stay low. That's an indication that we have buried water ice. And but when we are at this realm and where we may have ice underneath the surface, our spectrometers, the infrared and the mass spectrometer, are blind at the moment because they just see the surface. So this is where we have to drill. So the drilling is going to anchor our data. It's going to give us that third dimension. I mean, how else could we tell whether something is buried at the shallow or the deep or not at all? So during the drilling, the instruments work together in a different way. So the fields of view of the near-infrared spectrometer, visible camera, our thermal radiometer that measures surface temperature, and the mass spectrometer all overlap the drilling pile. So they're going to observe the soil as it's being brought up. And if water is present, it most likely will vaporize. And so the instruments are designed to identify the solid to gas transition, amongst many things. This concept has been practiced in laboratory. Shown here is we have taken a version of the drill and our instruments. You're seeing a camera on the left, the visible camera. On the right, you're actually seeing spectra. We had a vacuum chamber with lunar simulant, and we put water ice and other molecules in it. And the drill is extracting different depths, and while we're observing it spectroscopically. So this is how this concept came about. We did a lot of laboratory tests to get the right fields of view, the sensitivity. We did field work to help us out with the timing. But during the Viper mission, drilling is very expensive time-wise. It takes on the order of 5 hours, maybe 8 hours to do a drilling. And then if we want to sit and measure the subsurface temperature, that takes another couple of hours. So we're going to rely a lot on our USGS direction where they decide to do drill holes. You don't want to drill things one next to another. You often choose drill holes that are separated a lot, and then you look at what's known as a variogram. Again, I find all this geostatistical things fascinating, but you are tying all your data together to build up your picture. So anyway, that's our measurement approach. So I've mentioned the Viper rover and its smart payload and our mapping and measurement strategy. We still need to get to the moon. So introducing the Griffin lander from Astrobotic. So Viper is part of a different type of program at NASA where companies are providing essentially a FedEx service to the moon. So our Griffin lander will land us at our desired location within an error ellipse, of course. But as our traverse planning is inherently dynamic and responsive, we have the tools to create a new path regardless of where we land. In fact, our team right now is doing a trade between 5 different locations to kind of see where the best place the Griffin lander should place us. So where are we landing? So an infinite number of monkeys can type out the works of Shakespeare, or so the saying goes. So with a supercomputer, we can design hundreds of thousands of rover paths, but it does help to narrow the choice. So last year, we conducted a study of multiple landing sites near the lunar South Pole. We needed it to reach the plausible surface, subsurface, volatile areas, those ISR regions. We needed reasonable terrain for landing and roving. Again, we don't really know anything below the 1 meter scale, but we know at least something. We need direct view to Earth for our comms, and we need sunlight for power. So a decision was made in September, and we are landing. So the bullseye there is showing Shackleton Crater at the lunar South Pole. We're slightly north of that. We're going to be landing at the western ridge of the Nobili Crater, which is sitting up on a high plateau, which is great for sun and calm. So we're just zooming into that place. So we're basically landing on the western end of the Nobili crater. So let's take a closer look at the Nobili region. So we're going to study a surface area of about 36 square miles. We're going to travel between 10 and 15 miles over a period of about 100 days. And this is a reference traverse. We are looking at several right now, but it is very attractive because it's shown in pink here, because it's would bring the rover close to two large permanently shadowed regions, which are going to pop up as a light blue area. So those are where we think we have the surface ice, and they're accessible by the rover. So, and this is not the final traverse, we're working on several more. So unlike the Energizer Bunny, Viper has a limited life. We are designed to land in November or December of 2023 to the lunar South Pole, which is essentially the southern summer. And like seasons on Earth, there are times where the sun is a bit too low on the horizon, and the periods of darkness just get longer, and they'll get longer beyond our 50 hours of battery life. So sometime in March of 2024, or maybe April, if the topography is kind, wherever we've wound up, the shadows are going to stick around too long, and our little rover will slip into a dark sleep, or maybe we will just go like Thelma and Louise and drive into the deepest, darkest crater within reach and rove and rove and rove and take data until we run out of juice. We haven't made that decision yet. But when we're planning where the rover is going to go, we are looking to see wherever Viper eventually winds up. So Viper might wind up on a hill. We park it in the sun, and then eventually spring will come and the shadows will get too long, and the batteries will drain because it's in darkness for a while. Or maybe we'll be in the basin of a deep dark crater. But wherever we wind up, I hope we have that Apollo 12 Surveyor 3 moment again when our Artemis human explorers come and visit and find out where we wound up. So our leaps. 1609, when the moon became a real place. 1969, when we touched it and we brought back samples. 2009, when it surprised us with water on the moon everywhere, frosts, buried ice blocks, but we don't know anything about its nature, and its distribution is highly uncertain. So we're ready for this next leap. So Viper is going to give us that human scale detail of where the water is and how much is accessible. And when we have that part of the science of water on the moon, we could make those first maps to perhaps tell us the best place to harvest water. So my last slide, on the top left is, please, for the latest mission updates, come to our website. There's loads of opportunities to follow and participate during the mission. I showed the moon image of over San Mateo, California tonight, and Nobili is visible in a sense. This is a terrible scale here, but because we need calm from Earth, the Nobili region will be visible from Earth. In fact, on a blog site called Cloudy Nights, which you members may be very familiar with, Tom Glenn has taken a picture of the South Pole of the moon. This was done back in 2018. And I circle in the top right, the Nobili region, the Western, it's a high plateau. You'd have to image it when the lighting is favorable, because this was sort of taken when it's mostly in darkness. But it was only with a 9.25 inch diameter telescope and a CCD. So we're anticipating lots of moon gazers to follow us on our journey of exploration and to discovery of parts of the moon not explored before. So thank you for your attention. Thank you.
Well, thank you very much. That was a fascinating presentation. I apologize, I wasn't logged in when you first came on. My name is Mike Ryan. I'm president, but I've been having internet connection problems. So anyway, that's resolved for the moment. And we appreciate very much your presenting to us. Does anybody have any questions at this point?
Yes, Ken Lum. Does the drill heat up any of the soil and then cause a vaporization of water or other volatiles that can be detected by the detectors?
In a sense, yes, but it's and we're measuring that. So yes, there is. We have to have a measurement of the temperature that it's heating it up, especially if it hits rock, and can also try. It's both an auger and a percussive drill, and so we have different techniques to try to minimize that, but we are expecting that to happen. That in itself is an experiment of great interest to ISRU, because they would like to know the properties of the subsurface regolith, especially of how it reacts to thermal conductivity. And so we are, yes, we know that's going to happen. In fact, we will see losses that way. And we'll have to fold that back into our assessment of how much water was there to begin with.
Yeah,
okay.
This is Marion Weiler. Can you hear me?
Yes, you're
Yeah.
on, Brian.
Okay, yeah, I guess I had a question about the area that you're going to be exploring. Is anything known about the kind of the age of the surface or slight subsurface in that area? You talked about it's a high plateau. Does that indicate it's fairly recent structure of some sort, or do you really know? I guess it's since no exploration has been done there.
Yeah, I mean, its age, and I don't remember the exact age our geologist told us. It's not a very old place, but it's not a very new place. One of our hopes is when we're driving and we take some panorama images, and if we can see a recent crater, we'd love to be able to rove there and look at the recent ejecta to help us perhaps add some additional information. So it's old, but not super old. So it's just general age, but I know that's not really answering the question. How how you date on the moon is through the crater counts. And so that's how we know the age of where we're roving. And it's not particularly too old or too young. So, yeah, probably what, 3 billion years or so or more. We're hoping we'll go to those large PSRs are particularly attractive because the anticipation is they may be old, so they might have old ice or ice that's been around for a while. So we think there'll be a lot more of it there. But yes, when we got to restrictions from the comm and the lighting, it did really restrict us to where we could go. We did explore landing sites where the Artemis program wants to go, which is near the Shackleton crater, but those places were not trafficable. The slopes were too great. And we would have a very short mission. So from the mapping perspective, it didn't really work out very well because we wouldn't get enough data samples of the different types. But we're certainly not going to the oldest places.
Yeah. Okay. And I guess from the maps, I couldn't tell. At one stage, you talked about perhaps driving the rover into some of the craters, not necessarily the Thelma and Louise moment before that, but it looked like on the map projections, you're mainly outside of the craters on fairly level terrain. So is there any point where you actually are in a crater per se?
We want to be.
Drive down into a.
Yeah, but we have the rover has to cannot traverse slopes greater than 15 degrees. That's our design. And we have a lab at NASA Glenn in Ohio where the rover is driving up and down various slopes and it gets stuck and it has to climb up and all that. But we'll be taking pictures as we go to see whether there are craters that we can go into because they may have surface ice on them. And so those that we can go into safely, we will. But otherwise, we'll stay up as high as we can to get the mapping measurements. There's been an interesting discovery on the science team where it's very unknown. There's a metric in a crater. It's called the diameter to height ratio. And curiously, from the information we have to date, the craters at the south pole of the moon seem to be quite shallow on the small scales. The smaller the craters are, they're quite not so deep. And if that's the ratio is actually tweaked a little bit in that favor. So we'll have a lot of shallow craters. So we may actually be driving through a lot of them.
Great.
This is Stuart McHugh. I realize that to answer my question, you'd really have to have most of the data back from Viper, but you've mentioned a number of times discovery of water in various locations. Could you give us a better sort of example of what that means? Is it water locked in the crystalline structure of the rock? Is it, water like in the form of frost in the refrigerator? How recoverable would you expect it to be? And how much would you need, say, for astronauts to utilize it? Are we talking about 1 molecule of water per cubic meter or swimming pool worth? And I'm talking, of course, just what you can answer in terms of what's already been done.
Yeah, I mean, it's those are great questions. And so from the different measurement techniques from the orbits and the landers and the Chinese rovers that have found water on rocks. So the water on the moon has been in all different forms. So one of the things that Viper wants, the ground truth, is what form is the water in the places it's looking. So some water is in surface frost. Some water appears to be encased in glass beads inside lunar rocks, deep within rocks, which could be from the lunar interior. Some water could have been formed by solar protons hitting the moon's surface and then reacting with the lunar regolith themselves and creating hydroxyl OH. So water is implanted. It may have been there before. It could be in the solid water ice format. It could be intermixed with the soil. It could be blocks of ice. We don't know. It looks like it could be of all these different varieties. And so knowing the form of water is an objective of our mission to help identify or constrain these theories that predict, to try to explain the water signature. As to how much you need, gosh, I had a number. I lost where it was. It's not swimming pool amounts, but yes, I wish I knew that number. There is, a lot of predictions. If all the permanently shadowed regions actually had surface ice, if they did, it was translated to billions of tons of water ice on the moon, but we don't know if that's really an exaggeration. The current models predict that more of the water is probably more at depth. And so we want to find out how much of it is at depth, and if so, we can change the extrapolation. But I'm sorry, I've forgotten what the actual magic number is for how many gallons of water are needed to survive to be used for, a habitat of 4 people. There's all these different numbers. So
That's fine.
yeah, it's a squishy area because with in situ revisualization, it's not just about how much water it is, it's how much water it is and can I get to it? And the techniques to extract the water or extract the oxygen from the regolith, take a lot of heat or they take a lot of volume. It's mining in a sense, and that's a whole different area of active study. But my next talk, I'll have an answer.
I look forward to it. Thank you.
Bill Lockman has a question. You mentioned that there was our current knowledge of the layout of the site is to a resolution of 100 to 200 meters. Are there any plans for any missions preceding your Viper mission to improve the resolution?
Yes, there are. So LRO, which has mapped the entire moon at 100 meters per pixel, it also has a camera called the narrow angle camera, the NAC. The 100 meters per pixel is from the WAC, the wide angle camera. The NAC has gotten us down to 5 meters and 1 meter per pixel, but not all over the moon. But LRO is making more maps of the lunar South Pole as best they can. Their orbit is not ideal anymore. They've had to change their orbit slightly, but we will have some updated, as great information as possible, and we'll use it. But other than that, no, the other current orbital missions have basically on a few 100 meter per pixel resolution. So we wish we had better, but we're going to go with what we've got. And if new LRO data comes in, especially with these shadows, and they can help us more with our terrain, our topography, that would be great. But yeah, we have a few areas of 1 meter per pixel, so we're using that as best we can. The interesting bit is those images are good when there's a lot of light. When you have a lot of shadow, it's hard to see. So there's certain areas that we just don't have any information about.
Can radar be used to get better measurements of depth?
Yeah, so LRO has a laser altimeter called Lola, and that's mapped the moon at about 5 meters per pixel. Our team has been making photoclinometry products where they do shape from shading, where they're extrapolating between the 5 meter, so these pencil beams that are 5 meters apart from each other, and trying to get down to like a 1 meter prediction based on those 5 meters. So, and there's error bars, of course. Right. So yes, we do have sort of topography at the 5 meter per pixel, but nothing smaller than that.
Okay, thank you.
A question by Nelson. Hello?
Go ahead.
Go ahead.
Yeah, two questions actually. Will all or just some of the science that you glean from this mission be shared with the entire Earth, with all humanity, or is some of it planned to be kept in NASA's data bank only?
Oh, all the data is public, will be public. So all of NASA's missions puts their data in a public archive, the planetary data system, and all our data from our mission will be placed in those publicly accessible archives. So yes, all the imagery, all the spectra, that'll be made public.
Okay, thank you. And the other question, early on, you mentioned that parts of the moon are colder than even in Pluto. How do you explain that? Right.
So going back to LRO, this orbiter around the moon, that had has still in orbit, a thermal camera. And it's been mapping the temperature of the surface of the moon to a few hundred meters per pixel. So it still has that coarse scale. But it's been in orbit for almost over 12 years now, or 13 years now. So it's mapped the entire moon surface, and it's mapped the entire moon surface during all the lunar seasons, the summers and the winters, the days and the nights. So we have a pretty good map of the temperatures of the moon. What we don't quite have is the changes in the temperatures of the surface over short periods of time, because the diviner instrument on LRO would be on during certain parts of the orbit, and so when it would remeasure the same place, it could be months or years later. So our surface measurement from Viper, measuring just along our path, that's going to help anchor a couple of models on instantaneous, or what happens in a few hours after the sun goes away. How cold does it go? We don't have that information yet, but we do have sort of the static thermal map of the moon that is used as our guide.
And I guess my curiosity is, since Pluto is quite a bit larger, maybe there's internal heating that lends to the moon having actually colder areas than Pluto itself. Is that would that hold up in your knowledge of physics?
So both, but I mean, Pluto does have some internal heating, and the moon used to have internal heating. It still has some residual heating. In fact, the moon has a lot more what we'll call radioactive elements than, say, here on Earth. The creep, the K is for potassium. I'm losing my track of my elements. Thorium, potassium, thorium. So there is some residual heating on both areas. It's just the measurement that we've met that, these areas on the moon, even though it's closer to the sun than Pluto is physically, it just has not seen sunlight in billions of years. And it's just stayed cold, and there's not enough lunar heat now to warm it up from below.
Thank you. Thank you.
What is the design parameters that led to the decision for the 50-hour battery lifetime on this thing? And why not 75, or why not 25?
Oh, very good question. In fact, it used to be longer. We had to throw away a couple of bricks because our rover got a bit too heavy. Our drill got a little heavier, and then we had to lighten our rover. So we had to do a trade. At one point, earlier on in design, we had more what we called super bricks, more batteries, and then we could sustain longer hours in shadow, which was highly desired scientifically. When we had to solve the mass problem for our rover, because the drill got heavier, we had to lighten the load. And so we did a trade, and we found that, yep, 50 hours was good. We would have liked longer. But but that's what happened.
So if you lose power, is it possible to repower up again when the light comes back, or is it dead once it reaches a low enough level?
Well, right now, so how we're designing the missions, we've identified our, we call it mission success. We have covered the right coverage. We've traveled to all the different places we needed to get to. We are designing our rover's traverse to not have that ever happen. So we are biasing our places where we're going to prevent us from dipping in the danger zone. We want to always be power positive. And so even when we go into the permanently shadowed region and start to drill, and the drilling takes 5-8 hours, that's part of our 50 hours. It is a very mission critical activity. We are we're doing lots of trays right now on how to enter and exit and how to play with the shadows to prevent us from ever getting into the danger zone. But yeah, the solar is how we recharge the batteries. If the batteries drain, they may or may not get recharged. It's not how they're designed. They're designed to always have some sort of juice in it. Now, that said, the U-2 rover, the China rover, has survived lunar night, but their design is different than ours. They carry additional thermoelectric heaters. We couldn't, because our neutron spectrometer would not work as well. So we weren't able to carry an RTG like the Mars rovers or U-2 and survive a lunar night, because it would mess up our neutrons measurements. So we're stuck with an overly constrained problem.
So with respect to the lander, what sort of landing mechanism is going on here? Are you using the sky crane type system that the Mars rovers have used, or are you using a regular retro rocket system like the lunar module landing system is? And does that actually affect the local terrain in terms of what you will measure as you evaluate and assay the region around it?
Great questions. So we can't use a sky crane because sky crane requires an atmosphere. Well, actually, sky crane, well, the parachutes do. So yes, it's using primarily those retro rockets because we're going to land on an airless body. Contamination from the retro rockets, the type of fuel that they use, will affect our measurements. So we have a member of our science team whose job it is to evaluate the contamination from modeling perspective. And then we also won't believe or start our mapping until we're several hundreds of meters away from the lander, because we know there'll be a contamination area from, say, the hydrazine, which is throwing in hydrogen. And we don't want that to skew our, oh, there must be water there. So yes, so it's using, I don't know the details of the lander, but it's more like the retro rockets for the lunar landers of the past. But yeah.
Okay, and then my last question is, with respect to Antarctica, is the use of the resources that come out of there are constrained in the sense of what they can be used for and who gets access to it. Are there similar treaties with respect to access to resources on the moon, or is it a first come, first serve, whoever gets there first can do whatever they want to? And
well, there is a Space Act treaty that does talk about the moon, and I don't remember all the details of it. And also, it's applicable to the nations that have signed up to it. And recently there have been new clauses or directions from the agencies international agencies, NASA being one of them, particularly with forward contamination. So not necessarily dealing with the resources. Most of the attention has been on, are we going to destroy historic sites on the moon, like the Apollo landing areas, or are we going to mess up the radio quiet region on the far side of the moon? And as we have more and more voyages to the moon, and they may bring contaminants or biological things with them, what is that going to do to the ecosystem? That has been where the dialogue has been. As for the resource aspect, that is a lot of TBDs.
A lot of what?
TBD.
Oh, to be determined. Oh, yeah.
To be determined.
Yeah. So in fact, if SpaceX gets there first, is they can actually pollute and do whatever they're going to do. And since they're not a government agency and so forth, they're sort of outside the reach of any legal entity, I suppose.
Maybe. I haven't read the current act recently, but one could have that interpretation.
I guess we'll have
they seem to be willing to do that with respect to the small satellites and the
we'll have to invoke Starfleet's prime directive.
Yes. So can we follow the Antarctic model, which promotes an area for scientific research, and also which took a while to get to. Yes, very good questions. I'm hopeful that the appropriate behavior will happen, but we are having a lot more players planning to visit the moon in the next couple of years. It is a different era of exploration, and these Space Act treaties that the United Nations has put into place do need some dusting off and modernizing.
Okay, anything else, folks?
This is Marion Weiler. I had a question. It dealt with communication between the rover back to Earth. Is that kind of a direct to Earth, or is it up beam bounced off a satellite, or how is that going to work? And is that going to be 24 hours a day, literally, or is there some outages?
So yeah, it's direct to Earth. So there's no relay satellite, and there will be outages, and the outages occur when the Earth sets below the horizon. So in our nominal 100-day mission, this will happen about 3 times every sort of 28-ish days. We'll have 14 to 18 days of active operation, 24-hour Earth days, 24-hour Earth days for 14 days. And then we will be parked up on a high hill in the sunlight. So we're power positive, but we can't move because the Earth has gone below the horizon. And then we're going to have to sit there for 14 days. And then when the Earth comes back, we'll robe again. And that activity will be 24 hours for the period in which the Earth is visible. So yeah, it's a crazy intense period. And then we're kind of waiting. So that's how the operation is going to be. So we when we're looking at scientifically, we look at these periods of intense 24 hours a day for 14, 18 days, where we're collecting the data and driving and making dynamic decisions. And then there'll be another 2 weeks or so of the rovers just sitting there. But what the science team is doing is analyzing the data from the previous 2 weeks and coming up with where should the rover go when it wakes up, or when we have communication again.
Will there be some detection or measurements going on while it's sitting there parked in those 14-day quiet periods? Is it just collecting some data it can transmit when it's done, or will it truly being just asleep?
It will be in a sleep. It has very little storage on board. Clearly, it's going to have, during those 14 days, we'll be taking its heartbeat and its temperature data and a whole bunch of things and storing that. And so that will be the first thing that we will look at when COM appears. But when it's parked It'll do a localization with a star tracker, because that's another thing is we don't really, since there's no GPS around the moon, we don't actually know where our rover is really, but we're going to piece together a story by do localization with the topography and we are going to a regime in meters per pixel that we don't have data for. So when we're in the safe havens, those are nice anchor points. So the star tracker can tell us where we are at that point, and that could help with our geolocation as well. So, but that won't be continuous over the 14 days. That will just be like at the very beginning, and then the data will be stored, and then we wait.
Okay, and I was curious, last question I think for me is the staffing back at Mission Control or whatever on these intense 24-hour days for 18 days or whatever it is. Do you have like 3 full-time shifts of scientists monitoring this data feed that's coming in, or you've got one set of, like yourself, of course, scientists that are kind of there 8 hours a day or whatever, and then come in and try and process 24 hours worth of what's happened? How's that staffing and monitoring and so on? How's that going to work?
Yeah, no, we actually we have 4 shifts during those active periods, and we have a variety of folks in different roles for the decisions. There will be identified periods where key decision points are made. So, for example, one of our major activities is when we go to one of these ISR regions and we need to tell where to drill. We're going to pre-plan 2 of the drill locations based on our a priori knowledge, and then that's all about anchoring the maps. But the 3rd drill site, or maybe a 4th drill site in that vicinity, is a dynamic choice that takes advantage of the fact that we're just learning as we're going. When we staff up for those type of decisions, those are only happening, not all the time. They will be happening separated by several days. So, but yeah, we're staffed 3 shifts or 4 shifts with the science team with different roles, but there'll be surges and then there'll be quiet periods. There's one particular rover traverse design we're looking at right now where the rover is going to spend, 10 hours driving to in the dry. So during those 10 hours, are we staffed? It depends what else is going on. If we're noticing that the dry is more interesting than just being boring, but boring is, also, knowing where the dry is equally important to where the water is. So yeah, it could go either way. But yeah, we are carefully going through the staffing plan for how we're doing these shifts because it's very intense. Yeah.
We thank you, Kimberly, for favoring us with your talk, and look forward to hearing from you at some future time.
Thank you for inviting me, and
And,
follow our mission our mission updates. We're launching next year. Oh my goodness.